Okay, for this video I want to talk about the concept of conversion. And let's just look at our reaction we've been looking at in the last couple of videos. This SO2 and O2 reacting to form SO3. Now, if I put SO2 and O2 in a reactor and I let the reaction go for some time, it may be that not all of the SO2 and O2 reacts to form SO3. And that may simply be for many different reasons, but one common reason is that I did not let the reaction go long enough. So if I have 1,000 moles of O2, let's just write this out here, 1,000 moles of O2, and we'll assume it's in a stoichiometric ratio with the SO2, so 2,000 moles of SO2. If this goes fully to completion, 2,000 moles of SO2, 1,000 moles of O2 for full reaction, that should produce, forgot to put that 2 there, 2,000 moles SO3. Gotta make sure I have my right balanced equation and my stoichiometric coefficient set up properly, or I'm totally going to mess up the problem. And I did not have a balanced equation, now I do. So, going back to this example, if, again, 2,000 moles of SO2 and 1,000 moles of O2 are put in a reactor, if it goes full, the reaction goes full to completion, it should produce 2,000 moles of SO3. And that's the final product. However, I may not let the reaction go long enough. For instance, it may take 2 hours for this reaction from all these moles to react to form all of these reactants. Or excuse me, all of these products, all of these reactants forming all of these products. If I let the reaction only go 10 minutes, then there won't be enough time for all of these moles of SO2 and O2 to react to form the final product. And I may, for instance, get, in reality, 1,000 moles of SO3. And this is again because the reaction did not reach completion. And this is called a fractional conversion. It's not full conversion. Full conversion would be 100% of all reactants forming the products. And we can quantify this by, again, using some numerical formula. Fractional conversion is equal to moles reacted, moles fed. And conversely, percentage conversion is just 100 times fractional conversion. So I just take this number here and multiply it by 100 to get the percentage conversion. So let's look at an example of this. So going back again to my famous 2SO2 plus O2 going to 2SO3, and let's assume that we have a reactor and we start with 2,000 moles SO2 and 1,000 moles O2. And let's just assume this reacts to form 1,000 moles SO3. And we want to know what the fractional conversion is and the percentage conversion. We don't have to worry about what is in limit and what is in excess because these are in stoichiometric ratio, 2 to 1 here, just like here in the equation. But we need to figure out next is how much of the reactants we have left so we can figure out what we have remaining, and so we can figure out what's remaining so we can calculate the fractional conversion. So in this case we had 1,000 moles of SO3 produced. So I can just use the stoichiometric coefficient or stoichiometric ratios which are derived from the stoichiometric coefficients to find out how much is reacted. So let's just look at this here. If I get 1,000 moles SO3 produced, well, using the stoichiometric ratio of 2 moles SO3 produced per 1 mole of O2 reacted. This number here is just 500 moles of O2 reacted. Well, so again, looking at that, if I start with 1,000 moles and 500 moles reacted of the O2, that just means that this is going to tell me that I have 1,000 minus 500 equals 500 moles of O2 left. So that's how much moles of O2 I have after this reaction takes place. And I can do similar analysis based off the stoichiometric coefficients to realize that I will have 1,000 moles of SO2 left after the reaction goes. So let's look at this, put it all together. So here we have, again, summary, 500 moles O2 and 1,000 moles SO2 left. Again, we want to calculate fractional conversion, and that equals moles reacted, moles fed, and we can look at this, and that is equal to, let's just again go out analysis based off of O2. It doesn't matter because SO2 and O2 are in stoichiometric ratio, but the number of moles of reacted is 500 moles O2 reacted, 1,000 moles O2 fed. That's equal to 0.5. And that's our fractional conversion. And again, we can write percentage conversion. Multiply this number by 100, and that is equal to 50%. And there we have it. Some analysis on fractional and percentage conversion, and we'll get plenty of practice with this idea. Let me just end up one or two more comments here. In this case, it didn't matter which one we used. If we would have taken SO2 and plugged them into this equation here, we would have gotten the same number here. Sometimes in a problem statement, you may be asked to find the fractional conversion of the limiting reactant. And in that case, we would have to determine which is the limiting reactant, SO2 or O2. And if this was, for instance, in 3,000 moles per SO2, that means O2 would be limiting reactant and SO2 would be in excess, and then we could do the fractional conversion analysis based off of O2. Or whatever species is the limiting reactant. We can do it for other reactions also. But this is just useful, again, for helping us analyze what's coming out of a reactor after a reaction takes place. Fractional conversion or percentage conversion, because again, not all of the reactants will fully convert to the products.